I just wanted to add one more thing about platonic solids. Uh, there's sort of five of them here, plus this thing, which is two tetrahedrals interlocking with each other. But um, the platonic solids are solids that have identical faces and identical vertices and identical relationships between the edges. So each face is the same and each vertex is the same. This one's one that has three faces coming together and three edges on each face is a tetrahedral. One that has four edges on each face and three faces and three edges coming together at each vertex is a cube. An octahedral is one which has three edges on each face and four faces coming together at each vertex. And then there's slightly more complicated ones like the dodecahedral, which has five edges on each face and three edges coming together at each vertex, three faces also coming together at each vertex. And the icosahedral, which has three edges on each face, but five faces coming together at each vertex. But all the faces and all the angles are identical. And hopefully you notice that there's a lot of threes and fives going on, and that's all five of them that can exist. And I want to show a proof for the fact that there are only five of them using this formula. So it'll be an algebraic or a topological algebraic proof that f plus v minus e, as we already established, equals 2 for all convex polyhedra in three-dimensional space. So let's just check that relationship out. Here we have vertices, edges, and faces. So the two numbers in this column minus this number should always represent f plus v minus e, and it should always be equal to 2. So 8 minus 6 is 2. 14 minus 12 is 2. 14 minus 12 again is 2 for the octahedral and the cube. And the dodecahedron, you have 32 minus 30 is 2. And the same for the icosahedral. And I kind of want to show the proof using this logic. Let P equal the number of edges on each face, which is equal to the number of vertices on each face. So, and let Q equal the number of faces that come together at each vertex, or the number of edges at each vertex. Now, it's a fact that the number P, the number of edges on each face, times the number of faces, is twice the number of edges, because each edge is shared by two different faces. So you essentially go around to all the faces and count them all up, and you'll be counting each edge twice. And the same thing holds for the vertices. Each edge is connected by two vertices. So if you count the edges at each face, for every vertex, you'll be counting each edge twice. And so Q, the number of edges at each vertex, or meeting at each vertex, times the number of vertices is twice the number of edges. Then you can write this equation f plus v minus e equals 2 over again as in terms of only e, because you can set f equal to 2e over p, and you can set v equal to 2e over q. So then you just get, instead of f plus v minus e equals 2, you get 2e over p plus 2e over q minus e equals 2, always, always, always. And you can divide out the 2e, and you get 1 over p plus 1 over q minus 1/2 equals 1 over e. Or 1 over q plus 1 over p, or 1 over p plus 1 over q equals 1/2 plus 1 over e. 1 over e is always a positive number because the number of edges is always positive. So it must also therefore be true that 1 over p plus 1 over q is greater than 1/2. And this works for any case where you have the same number of edges on each face and the same number of faces coming to each vertex and the same number of edges coming to each vertex. Now, because every face and every edge are the same, or all the faces are identical, so you could take one of these figures here, platonic solid, and stretch it out, and then some of the faces would become longer than the other ones, and so forth. They would no longer be all identical. But since you can't do that and still have a platonic solid, then the relationship is preserved. And so you can make this table up for when the inequality is satisfied. And obviously, it can't be satisfied for, like, say, p equals 100 and q equals 100, because that's just 2/100ths. That's far less than 1/2. So p and q must be more or less small numbers, and 3 is the smallest number because that's the faces are in Euclidean space. They have to be, the smallest is a triangle with 3 faces, 3 edges on each face. So you can look through here. It obviously works for p equals 3 and q equals 3, the tetrahedral, because 1/3 plus 1/3 is 2/3, bigger than 1/2. All the way up until you get like a case where 3 and 5 are working together, and you have 1/3 plus 1/5. If you put that in terms of 15ths, that's 5/15ths plus 3/15ths, 8/15ths, still bigger than 1/2. But it fails once you get to 3 and 6, because that would just be, if you had 1/3, 1/3 plus 1/6, that would turn out to be 9/18, which is exactly 1/2. So that's basically the algebraic proof for why there can only be 5 platonic solids. I just want to throw that in there as one last final application for the Euler characteristic for polyhedra in three-dimensional space.